Okay, so we've gone through the conceptual models, and now we're going to start talking about gravity or mountain waves. First, flight hazards. And these flight hazards are very similar to the flight hazards we talked about with turbulence in our introduction to turbulence. Loss of control, structural damage, and passenger safety and comfort. So loss of control for aircraft flying through mountain waves and turbulent mountain waves can be a problem, especially for aircraft flying at higher altitudes. The higher you fly, the more your induced drag increases. The airspeed, the air is thinner up there. The airplane goes faster. So what happens is your stall speed increases with altitude, and your high-speed buffet or Mach buffet decreases with altitude. So they finally kind of reach together at high in the atmosphere. They reach a point where you really can only fly at one particular airspeed. And no airplane is certified to fly at that point, of course. What they do is they define an envelope that you can fly in. And the envelope is defined by the stall speed and also the Mach buffet. So if you're flying at high altitudes and the airplane experiences mountain wave or turbulence associated with mountain wave, you'll have airspeed excursions of 15-20 knots. And if you're flying high enough that you're up in that coffin corner, then you can have either a high speed or a low speed upset at altitude. And that had happened at the very early beginnings of jet aviation back in the 1960s and 1950s with aircraft. So that is a concern. Another thing that can happen is that the airplane may not be able to have or may not have enough roll authority to extricate itself or prevent the aircraft from flipping over if it finds itself in a vortice. These vortices happen typically at low altitudes. Also, you could see them at I wouldn't say high altitudes, but mid altitudes also associated with mountain waves. We'll talk more about where to find these vortices. But there have been cases where accident investigators theorized that an aircraft accident was a result of the aircraft being flipped over and then nosing into the ground. So that is a concern and a problem. And then another loss of control problem is when when the downdraft exceeds the performance capability of the aircraft. In other words, you can't climb. And that happens with strong updrafts, but more importantly, with strong downdrafts near the ground. This was the case, at least that's theorized, with the death of Steve Fawcett, who departed in a Santabria in California and was flying in mountainous areas close to the terrain when he experienced a strong downdraft and was pushed into the ground. They found him, I can't remember how many months later, about 4 or 5 months later, they did find his aircraft and his body. And then, of course, structural damage. We've gone through in the introduction to turbulence, the structural damage that can happen to aircraft, and it does happen in mountainous areas also. Here's a specific case of a DC-8 that was flying over the Colorado Rockies west of Denver. It experienced not moderate, but severe to extreme turbulence, clear air turbulence. The right outboard 19 feet, I think it was 19 feet, of the left wing departed the aircraft as well as the number one engine. Encounters with severe turbulence, mountain wave turbulence, can cause structural damage. And then, of course, passenger safety and comfort. We talked about how often turbulence causes injuries to passengers. This is especially the case over mountainous areas. This accident specifically happened back in 2014 over Sheridan, Wyoming, near the Bighorn Mountains of Wyoming. It was a United Airlines aircraft, and in this case, a number of people were injured. It says, I highlighted some of the areas. There was a lot of screaming. One woman hit the ceiling so hard that her head cracked the panel above her head. And another woman called out for her baby, who she lost control of. The baby was bouncing through the aircraft. That's pretty scary. Here are some accidents that have happened in the past that resulted in aircraft damage or crashes. So what we're going to do now is we're going to talk about the characteristics of mountain waves or gravity waves. And the first that we're going to discuss is just more or less general, the turbulence that's associated with mountain waves. And usually, if it's severe to extreme turbulence doesn't last very long. It's very short-lived. Usually, severe to extreme turbulence doesn't cover a large area. It's usually very localized, but it can be extremely violent to the point where it could cause structural damage, as you can see to this B-52. I hope you watched that video, because it was really interesting how they landed a B-52 with no vertical stabilizer, or rudder for that matter. This is a study that was done in 2008 at the National Center for Atmospheric Research by a UND graduate, Jamie Wolf, and also another researcher, Dr. Sharman. And they looked at the climatology of mountain turbulence and how mountain wave turbulence was distributed seasonally and also not temporally, but spatially across the United States. So first off, before they even looked at mountain turbulence, they looked at all turbulence reports above 18,000 feet, flight level 180. Not all reports, but reports of moderate or greater turbulence. And it was normalized, meaning that they took the number of moderate or greater turbulence reports and divided it by the total number of reports to help give you kind of a percentage. And this is what they came up with. And the areas of red show you where there is more turbulence above 18,000 feet. And you can see some areas of red are over Florida, over Texas, Colorado, even Wisconsin. And if you work your way into Utah and up west into the Pacific Northwest, you can see regions where there's a lot of clear turbulence, high incidence of turbulence at high altitudes. Now, what they did was they took those same pilot reports and only looked for, in the remarks section, mountain wave. When they saw mountain wave in the remarks section, they took those turbulence reports out and plotted them and normalized them also by the total number of reports, and came up with a picture of where mountain wave turbulence occurs. And typically, you see mountain wave turbulence across Montana, Wyoming, and Colorado, and also parts of Nevada and Idaho too. But you really don't see much turbulence at high altitudes across the Appalachians, nor across, well, of course, Texas. You don't see really anything there. We saw areas of higher turbulence over Texas and Florida, but those are probably caused by other reasons. This is strictly mountain wave, looking at the remarks section. And the black lines that you see here are the terrain elevation in increments of half of a kilometer, or 1,650 feet. And you can see that in Colorado, where you have the highest terrain, and also across Montana, that's where you tend to have also the highest occurrence of mountain wave remarks or pilot reports. So just compare the two, and you can see that mountain wave really steps out with relation to the terrain features. So just to summarize, mountain wave turbulence is confined to the western United States. You don't see it over the Appalachians, but there's not a lot in Washington or Oregon. And it seems like the highest frequency of mountain wave turbulence reports are across Montana, Wyoming, Idaho, Colorado, and Nevada and Utah. Here's the same study. They looked at the time of year that these mountain wave pilot reports occurred. And you can see that you have a pretty good frequency, pretty high frequency between January to June, or actually May. It kind of drops off in June and August, and through June, July, August, and even into September. October is pretty low, but it starts coming back again. It looks like maybe after October into November. So, most mountain wave turbulence pilot reports happen between November and May. And the peak is during December and January. And that is when you have the highest frequency of mountain wave. That's when you see mountain wave, December and January. And that's a result of the strong jet streams that you find during the wintertime that come out of Canada. The jet stream isn't up in Canada during the summertime, but it drops down with the cold air across the continental United States during the winter. And of course, it's the strongest. The jet streams are the strongest in December and January. And then here's another part of the climatology report. They showed that moderate or greater mountain wave turbulence occurred most frequently when the winds were between the southwest and the northwest, between 240 and 310 across the United States. But the peak frequency, if you look at those little black histograms, and it looks like the peak frequency is right about 270. So in other words, when the winds are out of the west over the mountains, you tend to have mountain wave. And if you look at the United States, most of the mountain ranges across the United States and the western United States are north-south oriented. So it does make sense that when the winds are out of the west, you tend to have more wave activity. So in summary, the climatology, of course, mountain wave turbulence is favored with strong westerly winds. Those are more common during the winter months, and you'll find it in regions. You'll find mountain wave turbulence typically in regions where the elevations are more than 5,000 feet, MSL. Okay, our last section in this video deals with the terminology that we use when we talk about mountains and mountain wave. So the first thing you need to know, and I think most of you probably realize this, but a wave has a wavelength, which is measured from the crest to the crest or from the trough to the trough. It's usually measured in kilometers when we do research. The amplitude also is how high the wave extends. And typically waves can extend all the way through the troposphere into the tropopause and well into the stratosphere. They've been documented up to 60,000 feet. Two other terms that you need to be familiar with are windward and leeward. Windward means the upwind side of the mountain. Leeward means the downwind side of the mountain. And then finally, when we talk about a standing wave, that's one that does not move with time. That's the last video on mountains and mountain wave, and I hope you enjoyed this.